Got it. Better? Okay, so high contrast instruments theory. So this was great fun. I get to talk about theory. I get to say nothing practical for the next 45 minutes. But I'm trying to inject a couple practical things here and there. It's 45 minutes to go through the whole theory of high contrast instruments is actually really hard. So I definitely have too many slides. Not as deep a dive as I would like in some of the math, but there will be math, I promise you, because I'm a professor and that's fun. But I wanted to get everything in here so when you download it, you have a reference and you can look at places. Although I realized I forgot to add a reference list at the end with the actual paper. So I will try to do that over the course of the next week and make sure the final version actually has papers you can go to. So with that, we're going to start at the real basics. I'm going to be very professorial. I start at this absolute simplest, defining the problem. So I apologize if this is really simple. And then looking at the solution. So here's the problem, of course. We have a star that's really far away, and we want to image it through a telescope. So if you look at just simple ray optics, you have a point source. When you're really far away, all the rays are parallel. They go through a lens. And you image your point source, and that's your star. If you add a planet next to it, well, those rays come in at an angle, and the planet gets imaged at a slightly displaced position from the star, and lo and behold, you have your planet, and you have your star. So, of course, this doesn't work this nicely because we have to account for diffraction. So here's my first equation. I would have drawn Huygens wavelets here, but that would have taken a lot more time. So this is actually using the solution of Maxwell's equations and Green's functions. I refer you to Goodman for this. But the basic idea, of course, is you have an opening, you have a planar wave. So all those rays we're now treating as waves. So the waves are perpendicular to the rays. They hit an aperture, and every point in the aperture can map to another point out in some plane a distance z away with some angle theta. And when you're all done, this input electric field, E1, in this plane produces an output electric field through this equation, which is the Huygens-Fresnel principle. And this is a sort of a picture of what happens, and you can see all the interference patterns or the diffraction pattern that results. So everything starts from here. Everything I'm going to show you starts from here. We now use a wave. This would be the aperture of your telescope. This, of course, is way too hard to solve any practical problem using this, so we look for certain approximations. And there are several important approximations that are made. The first is in what we call the very near field. If we're really close, we can approximate it by this equation, which I'm not going to spend any time on. A colleague of mine, Bob Vanderby, coined the term S. Huygens. If you get sort of in the reasonably near field, so these numbers are defined, these are all determined by what's called the Fresnel number. So if the size of the aperture divided by the wavelength times the distance is of order 1, you're in what we call the Fresnel regime, and it reduces to this, which is actually a Fourier transform also, but it has this term that's quadratic in the exponential in the independent variables across the aperture. And if you go really far away, and this means really far away, you can let z go to infinity in this exponential, and the quadratic term you just assume is really small compared to the linear terms, and you end up with the Fraunhofer equation, which is just a Fourier transform of the electric field in your opening. Fortunately, if you have a focusing lens like in those other pictures, it reproduces exactly the Fraunhofer regime. So you're in a Fourier transform. So almost everything we're going to talk about with coronagraphs is just a Fourier transform. I'm not going to really say anything except for one little spot that involves these more complicated integrals. It's amazing how much people have done in high contrast imaging just using a Fourier transform. So it's all based on the Fourier transform of your entrance aperture. So once you have the basic optical theory down, basic math, you can come to our real problem, which is imaging a star and a planet with diffraction. So I'm sure this is all sort of optics 101. You have an input field, you have a lens, which I'm going to define by a function a of x. So a of x could be a continuous function, or normally it's a binary function. It's 1 where light gets through and 0 where it doesn't, so it could be a circle function or a rectangle function. It defines the shape of your telescope entrance aperture. What you get in the image then, this is the ray optics picture, is just the square of the Fourier transform of the input field times this function. That's this Fourier transform. Right? So this is it. This is what we call the point spread function. The square because, of course, detectors detect intensity, not field, so you have to square it. If you have a planet, then it's just given by the Fourier shift theorem. The waves are coming in at an angle which looks like this. Well, that's just sines and cosines. And the Fourier shift theorem says if you take the Fourier transform of something times the sine or cosine, the result is the same Fourier transform shifted by the argument of the sine or cosine. So this just shows that if we have an off-axis source, it just gets shifted off to the side. So now we're looking at these point spread functions. So if we have a simple circular telescope and we take the Fourier transform of a circle, you get the area function. And it looks like that. So that's our point spread function, right? All these concentric rings. So of course, the problem with imaging planets is that the planet has this same pattern, but off to the side. And this is, of course, resolution, right? This is what the resolution of a telescope is. The size of this central core is given by the size of your entrance aperture. The bigger the aperture, the smaller this little central core. This second ring here is about a factor of 1,000 below. This is a log scale, so you get to see a lot of rings. But it's about a factor of 1,000 between these two. So if you're just doing simple astronomical imaging, you usually don't care about anything but this central peak. So resolution is how far apart you can see two objects before those central peaks overlap. That's the resolving power of your telescope. So the interesting thing about exoplanet imaging is it's not a resolution problem. Right? So here's that picture. Here's just a cross-section through the area function. This is a 2-meter telescope in visible wavelength. This is a 10-meter telescope. But even at 2 meters, you can see these two peaks. If the planet were really bright, you'd see it next to the star. They're not that 1 AU at 10 or 20 parsecs is enough of a separation that with reasonable sized telescopes, certainly even space telescopes, you could resolve the two objects. So the problem is not one of resolution. It's one of contrast. Right? The problem is, so here's a typical example of a star at 10 parsecs at 1 AU, and you can see the planet is out at around the third or fourth area ring. So it's not a resolution problem, it's just much dimmer. And that's the high contrast problem, right, of imaging exoplanets. The planet falls many orders of magnitude, like a million, factor of a million, below the third, fourth, fifth, sixth area ring of the star. So even though their main lobes are separated, you've got all this starlight from the stellar halo blocking the planet. So that's the problem of high contrast imaging, or high contrast instruments. How do we do that? How do we get rid of that light? Now, in principle, and this has come up a couple times this morning, and I'll get back to it again a little bit later, in principle, if everything was perfectly stable, and you knew exactly the shape of your telescope, and there were no errors, and I knew this thing perfectly, I could just subtract this point spread function out and get the planet, as long as I have a lot of dynamic range and a ridiculous number of bits in my computer, because I need to carry all the precision in order to see a million times different, and I could integrate forever because I'm going to have a lot of photon noise associated with all this for my really dim planets. But in principle, you can do that, and that's that problem people referred to today of PSF subtraction, right? At some point, you're getting the planet out by understanding the PSF of your star and getting rid of it to find the planet. And a remarkable number of these discoveries you saw this morning were done by doing just that. But the problem is this dynamic range is too bad, so you've got to get rid of all these photons so you're not dominated by photon noise and just the well depth of your detector and the number of bits you're using to digitize it. So the problem of high contrast instruments is we typically want to get this halo of the star down to around the level of the planet. We call that a Q of 1, the ratio of this intensity to that intensity. We want it to be about 1. And then you still have to do PSF subtraction, because if you looked at that, you wouldn't see the planet. I mean, so all of these techniques at some point are going to use some sort of data processing and PSF subtraction. I'm not going to talk about that. You get to hear that later. I'm going to talk about how do you do the first step. How do you get it so that you're at least operating in a regime where you're not dominated by stellar photons, and then you can think about these data processing techniques. So before I go into the general theory of that, I thought we'd start with an example. It's always good to start with an example. And the classical, most famous example. Oh, wait, forgot about this. I'm not there yet. Sorry. So to understand high contrast imaging, we need to understand these, how many are there? 5 things, right? So the contrast is what I just talked about. It's the ratio of the peak of that stellar point spread function. So it's the ratio of this number to that number, which you might say is really silly, because I just got through talking about this ratio being important, right? But this ratio sort of depends on where the planet is, depends on the size of the telescope as these area rings move in and out. This ratio is defined by the physics of the system. And so most people talk about contrast as the ratio of the peak of the star to the peak of the planet. We call that the contrast ratio. And so we have to design a system where we can operate with that contrast ratio. The inner working angle is the smallest angle in the sky at which the needed contrast is achieved, and the planet is reduced by no more than 50% relative to other angles. So we're going to come back to that quite a bit. So the idea is we want to take that stellar halo and we create contrast in our instrument by lowering it to the point of where the planet is. The amount we lower it relative to the peak of the star is called the instrument contrast, or the contrast ratio of the instrument, right? But if you did that and at the same time eliminated the planet, it wouldn't be a very good coronagraph. You would have created fantastic contrast and you'd see nothing. So you also have to have a reasonable amount of throughput through the system. That's this number. So the planet's actually getting through the system with enough photons that you can detect it. And so there's always a balance between these three things, that trying to create contrast at a small inner working angle while still having enough throughput. And then this 50% number is just sort of an arbitrary definition people came up with many years ago for the inner working angle, that beyond that, the light from the planet starts to drop off so much, it's just not practical to pull the planet out. And hopefully we'll see how that works. And then bandwidth, it's actually really easy to design a coronagraph that works in laser light. It's just, there's lots of them, and it's just not that hard. Designing a coronagraph that works over a reasonable number of wavelengths, so you get it, photons, you can do color, that's hard. And for a whole variety of reasons, some of which I'll touch on theoretically as we go through. So this becomes critical, is what are the range of wavelengths in which you've actually accomplished creating high contrast that you can detect the planet. And then sensitivity, this is the practical bullet, so I'll talk very little about that. But you're going to embed this thing in a telescope, either on the ground or in space, and there's atmosphere, and there's real optics, and the spacecraft's moving around. How does your performance degrade in the presence of all these real errors? Aberrations due to the optics, aberrations due to the atmosphere, mispointing, and different coronagraphs react differently. They have different sensitivities, and this becomes critical when you actually think about building a real system. So everything we're going to do when we talk about how chronographs work, we're always going to keep in mind these 5 performance metrics. One thing about throughput that's a little bit interesting is when we all started in this field, we mostly talked about this, the ratio of the open area of the telescope remaining. So what you're going to see is that every coronagraph blocks some of the aperture. It's impossible to make a coronagraph that doesn't block some of the light. You can't get 100% of the light through the system. But that's not necessarily the best measure of contrast, because if you go back to our area function picture, when we're actually doing PSF subtraction or whatever technique to pull this planet out, we're usually only operating with the main lobe. The halo of the PSF of the planet contributes almost nothing to getting it out of the background. Those of you who have taken stellar image or stars out of the background know that it's really only the main lobe. So the problem is a lot of coronagraphs throw a whole bunch of light out here, and that becomes useless. So what we really want to do when we talk about throughput is not talk about all the light of the planet coming through the coronagraph. We want to talk about how much light's landing in that main lobe of the planet's PSF. So that's really the more interesting throughput. And I got a slide later about the various different definitions of throughput. And different coronagraphs make better or worse PSFs. So these are all the things we trade off when we're designing. Okay, so I'm going to talk about coronagraphs. Aki was going to follow and talk about star shades, 2 different ways of creating high contrast. And then tomorrow, Laurent is going to give a fantastic talk about how you get the planet out, that whole PSF subtraction thing. So I'm not going to really talk about any of these 2 things, but it's nice to remember that, again, once we've gotten to that point of lowering the halo, creating contrast, you still have to get the planet out. And there's still a lot of background from the stellar halo. Okay, so coronagraphy. So a coronagraph generally now is defined as anything that modifies the optical path of the telescope to reduce the stellar halo in what we call the discovery zone. There's going to be some region of the image plane in which we create high contrast, and that's where we'll be able to find the planet. This has gone beyond the original definition. It's called a coronagraph because the very first one, which is what we're going to start with, that's my example I mentioned a couple minutes ago, was a device built by Bernard Lyot in the 1920s to look at the solar corona. So hence the name coronagraph. How do we create an artificial eclipse? Block the center of the star, see the dim corona that's around it. And so he made the very first coronagraph, and we've expanded that word to now refer to anything that's inside of a telescope that uses various optics to do the same task, and in our case is to find planets. So this is that very first coronagraph, the Lyot Coronagraph. Beth showed a different image. I found this one that I think is kind of nice. So how does it work?